Welcome to 8th lecture of module 2. The module 2 is on mass transfer coefficient. So, we are discussing the interface mass transfer. We will continue in this lecture the interface mass transfer. In the previous lecture, we have considered the material balances in a two phase contact equipment to obtain the operating line. Operating line equation, and this we have discussed for two cases. One is counter current operation and second one is co-current operation. And we have seen that among these two operations, counter current and co-current, the counter current is preferred because the average driving force for mass transfer in case of the counter current operation is more compared to the co-current operations. So, it is favorable for mass transfer operations the counter current mode. Today, we will discuss the stage wise contact of the two phases. So, here our objectives is to define concepts of stage, ideal stage, and cascade, and secondly determination of number of stages in a cascade required for a given separation. In general, in a stage wise contact operations, the liquids are fed at the top of the column and the gas fed at the bottom of the column, and they are in contact each other and the phase flows in opposite directions. It is generally in a tray or packed column. Phases are in contact in packed or plate columns. Then what is stage? When two immiscible phases are brought into contact in any device or combination of devices to achieve mass transfer from one phase to the other. And is called a stage. So, what is then ideal stage? If the immiscible phases are in efficient contact in a phase and the leaving stream are in equilibrium. So, then we call the stage is ideal stage. If the immiscible phases are in efficient contact so that the leaving stream are in equilibrium. In that stage, then the stage is called ideal state. If a group of stages are interconnected, so that the phases are moved from one stage to the other, then we call that cascade. So, cascade, a group of stages interconnected so that the phases flow from one to the other is called cascade. So, cascade in most of the cases are required, because in one stage it may not be possible to obtain the desired separation. So, in a cascade we can achieve, depending on our separation requirement, we can decide the number of stages required for the given separation, and so cascade is effective in a particular separation. Now, we will consider how to determine this number of stages in counter current operation. First, we will consider the graphical method and then we will consider analytical method. So, graphical method is most convenient when single component is transferred. Now, consider our earlier columns. We will consider tray columns. So, gas inlet at the bottom, and we consider bottom it is n stage, stage number n, this is n minus 1, and this is the liquid in at the top of the tower like previous conventions. This is L 0, L s and x 0, and this is stage number 1, and gas out from stage 1. So, this will be G 1, G s and Y 1. So, here is x 1 and the liquid from here is Y 2, this is 2, and this is the liquid coming from this stage x 2, and suppose this is the n minus 1 tray and this is nth tray, small n, any arbitrary location, and the gas in from G n plus 1 and G s and Y n plus 1, and liquid coming out from this tray which is nth tray is L n, x n and L s. So, it is x n and going out is y n. So, if we do the material balance over the envelope 1, and this is the overall envelope, say 2, so if we do the material balance, we can write for n trays it will be G s y n plus 1 minus y 1 will be equal to L s x n minus x 0. This is the equation of operating line. Similarly, overall mass balance for a particular component in envelope 2, we can write G s y n plus 1 minus y 1 will be L s x n minus x naught. So, this is also equation of straight line passing through points x naught y 1 and x n y n plus 1. Now, if these plates are ideal plate or ideal stage, then y star will be equal to function of x. Now, we can plot the operating line and the equilibrium line. suppose this is y star is equal to function of x, this is the equilibrium line, and the operating line mass transfer from gas to the liquid. Suppose this is our point which is r and it is x n y n plus 1 and this is x and this is y, this is 0 and this is point q. QR is the operating line and this point is q point is basically x naught and y 1. Now, to obtain the number of stages or plates using the graphical method, we can proceed step by step. From point R, we can draw a vertical line which is crossing equilibrium line at point S, and then we can draw horizontal line from the equilibrium line. So, this is at T. So, the first step start at point x n y n plus 1, that is the bottom of the column, and then draw a vertical line through R which meets the equilibrium line at point S, which is x n and y n. Now, third step is to draw a horizontal line through S which meets the operating line at point T, which is x n minus 1 y n. So, this is the first 3 steps we followed and we obtain R S T. So, this R S T stands for an ideal plate. So, the region R S T stands for an ideal stage. Now, we can proceed successively drawing the vertical line and the horizontal line. So, this is n, this will be n minus 1. Similarly, we can proceed this way, we can obtain the total number of stages required. So, by drawing successive vertical and horizontal line segments, between equilibrium and the operating line gives the number of ideal stage. And these operations will end at point Q, which is x naught y 1. So, this is the graphical method of solutions to obtain the number of ideal stages. Now, we will discuss the number of ideal stages, how we can determine by algebraic method, and which is commonly known as the Kremstar equation. In this case, if both the operating and the equilibrium line are straight, then we can be able to obtain the number of ideal stage by algebraic method. Doing the same component balance, referring the same figure, we can do the overall component balance. That is L s x naught plus G s y n plus 1 is equal to L s x n plus G s y 1, and from this we can write L s x naught minus G s y 1 will be equal to L s x n minus G s y n plus 1. Similarly, for component balance, say this is equation 1 over n plate, we can obtain L s x naught plus G s y n plus 1 is equal to L s x n plus G s y 1, and from this we can obtain L s x naught minus G s y 1 would be equal to L s x n minus G s y n plus 1. So, if we compare between 1 and 2, we will get L s x n minus G s y n plus 1 will be equal to L s x n minus G s y n plus 1. Now, from this we can write L s into x n minus capital X n is equal to G s y n plus 1 minus y n plus 1. As per our assumptions, equilibrium line is straight. So, we can write y n plus 1 is equal to m x n plus 1 and y n plus 1 will be m x n plus 1. Now, if we substitute in this equation, it will be L s x n minus x n is equal to G s m x n plus 1 minus y n plus 1. After rearrangement, we can write x n plus 1 minus L s by G s m x n is equal to y n plus 1 by m minus L s by m G s into x n. So, if we define L s by m G s is equal to A, which is known as absorption factor. It is the ratio of L s by G s divided by m, ratio of the slope of the operating line to the equilibrium line. Then we can write this above equation will be x n plus 1 minus A x n is equal to y n plus 1 by m minus A x capital N. So, in this equation right hand side is constant and this is linear first order non homogeneous difference equation. This can be solved by finite difference method. So, we can write the corresponding homogeneous equation x n plus 1 minus A x n is equal to 0. The general solution of this is x n will be equal to C 1 into z to the power n. C 1 is constant . If we substitute this equation in the original equation, we can write C 1 z to the power n plus 1 minus C 1 A z to the power n is equal to 0, and from this we can write z equal to A. So, the solution is x n will be equal to C 1 A to the power n. Now, since the right hand side is constant, the particular solution is x n is C 2, where C 2 is a constant. Now, if we substitute both these things in the original equation, we have C 2 minus A C 2 will be equal to y n plus 1 divided by m minus A x n. So, from this we can obtain C 2 will be equal to y n plus 1 divided by m minus A x n divided by 1 minus A. So, the complete solution we can write x n will be equal to C 1 a to the power n plus y n plus 1 divided by m minus A x n divided by 1 minus A. Now, if we set n equal to 0, then C 1 will be x naught minus y n plus 1 by m minus A x n divided by 1 minus A. So, therefore, x n will be x naught minus y n plus 1 divided by m minus A x n divided by 1 minus A into A to the power n plus y n plus 1 by m minus A x n divided by 1 minus A. So, this is a very useful equation to generate concentration x n at any stage if we know the terminal concentrations. Now, putting in this equation n is equal to n plus 1, we can obtain several forms. First, we will consider mass transfer of solute from gas to liquid, say in case of absorption. So, in this case 1, A absorption factor not equal to 1, we can write y n plus 1 minus y 1 divided by y n plus 1 minus m x naught will be equal to A to the power n plus 1 minus A divided by A to the power n plus 1 minus 1, and the number of stages n we can write log of y n plus 1 minus m x naught divided by y 1 minus m x naught into 1 minus 1 by A plus 1 by A divided by log A. So, and case 2 A equals 1. In this case, we can write y n plus 1 minus y 1 divided by y n plus 1 minus m x naught will be n by n plus 1, and n will be, we can write n will be y n plus 1 minus y 1 divided by y 1 minus m x naught. Similarly, mass transfer from liquid to gas, we can write case 1 A naught equals 1, it will be x naught minus x n divided by x naught minus y n plus 1 by m will be equal to 1 by a to the power n plus 1 minus 1 by a divided by 1 by a to the power n plus 1 minus 1, and we can write n is equal to log of x naught minus y n plus 1 divided by m divided by x n minus y n plus 1 divided by m into 1 minus a plus a. So, this divided by log 1 by a. Now, for case 2 a equals 1, we can write x naught minus x n divided by x naught minus y n plus 1 by m will be n by n plus 1, and n is equals x naught minus x n divided by x n minus y n plus 1 by m. So, these are the different cases for absorption and stripping. In particular, we can get the number of stages and the concentrations in different stages we can obtain. Now, if we consider mass transfer in cross current operations. So, we will consider 3 stages connected in series. And in which the gas is flowing from one stage to the other, and in each case fresh liquid is introduced. They may be of the same initial concentration or in varying concentration. Let us consider same initial concentrations of the liquids are fed. So, this is G naught, G s, Y naught, Y capital naught, and L naught, L s, X naught, capital X naught, and liquid leaving L 1, L s, X 1, capital X 1. This is G 1, G s, this is 1, this is 2, this is 3, and Y 1, capital Y 1. This is L 2, L s, X naught, capital X naught, and this is leaving X L 2, L s, X 2, capital X 2 and L3 LS X naught capital X naught and leaving at L3 LS X3 capital X3 and this gas is G2 GS Y2 capital Y2 and this is G3 GS Y3 capital Y3. So, similar way if we do the mass balance, we will obtain the slope of the operating line is minus Ls by Gs. So, this is similar to the co-current operation, the slope of the operating line, that is in individual stages in the cross current operation, the stages are in co-current in nature. So, we can plot the equilibrium line and operating line XY diagram. Suppose this is your equilibrium line and this is the inlet point, or this is x naught and this is y naught. So, with a slope of minus Ls by Gs, it can touch to the equilibrium line and then we can go horizontally and this will give you y1 and from this with the same slope we can obtain this line. So, this will give again y2 and from this we can obtain y3. So, this will be x3, this will be x2 and this will be x1. So, this way we can obtain the number of stages required in case of cross current operations. Let us take a simple example. A refinery of gas streams contains 10% undesirable component B. It is desirable to remove 95% of component B. The feed gas streams enters at the bottom of a separation column at a flow rate of 5000 kg per hour. The pure solvent is fed at the top of the column at a flow rate of 5000 kg per hour. The equilibrium relation is linear, y is equal to 1.1 x. Obtain the equation of operating line and calculate the number of trays by graphical and algebraic method. So, as we can see, this is a counter current operation and the concentration of solute which to be removed is given as 10% and we have to remove 95% of component B which is undesirable, and both the liquid and the gas streams their flow rates are given. So, feed concentration is given is equal to 10%. We can write on solute free basis. We can obtain Gs will be 5000 which is G into 1 minus 0.1, 10% is 45 not kg per hour. Mass of solute entering is 5000 into 0.1 is equal to 500 kg per hour, and 95% removal of component B. So, feed concentration y n plus 1 will be 0.1 divided by 0.9, which is 0.111, and exit concentration would be 0.111 minus 0.111 into 0.95, which is equal to 0.006. The solvent is pure. So, x naught is 0. So, the material balance G s will be y n plus 1 minus y 1 is L s x n minus x naught. So, putting the values 4500 into 0.111 minus 0.006 is equal to 5000 x 1 minus 0. So, we can get x 1 is 0.0945. So, x 1 is known to us. Now, if we do the material balance over the envelope 2, so G s, as considering the previous figure, y n plus 1 minus y 1 would be L s x n minus x naught, and x naught is 0. So, from this we can get 4500 y n plus 1 minus 0.006 will be 5000 into x n. So, from this we can get y n plus 1 will be 1.111 x n plus 0.006. This is the equation of operating line. So, we know the equation of operating line, and we know the equation 1.1 x with a slope 1.1. So, we know the slope of the equilibrium line. This is equilibrium line. Then we can graphically obtain, like previous method, we can graphically obtain the number of stages by plotting vertical and the horizontal line. Now, if we use the Kremser equation, which is A is equal to L s by m G s, which is L s is 5000 by 1.1 into 4500, which is 1.01. Now, n, if we substitute, which is log y n plus 1 minus m x naught divided by y 1 minus m x naught into 1 minus 1 by a plus 1 by a divided by log a. Now, if we substitute, it will be log of 0.111 minus 0 divided by 0.006 minus 0 into 1 minus 1 by 1.01 plus 1 by 1.01 divided by log 1.01. So, this will give around 16 number of plates. Thank you.